Okay, everybody. So welcome back. We are in the home stretch for the course now. So we are basically going to knock out most of the supplemental topics, so that by the end of this, we will have essentially done absolutely everything in the notes. There's like a couple sections that we won't go over, but pretty much we've hit everything, and definitely all of the big stuff, all the meaty stuff we will have hit. So for this next topic, uh, wanted to revisit Markov chains. Um, so our previous treatment of Markov chains, um, we handled a lot of the basics. We had this big, powerful theorem that in the case that our transition matrix was regular, we got a really, really nice thing about the steady state vector. And we had this like powerful theorem that we could use in the regular case to say a lot of nice things. And what made it nice was that the steady state vector didn't depend, well, among other things, didn't depend on the actual initial vector that we chose. So I could say a lot of good things about it. But we saw even in the material that we already did on Markov chains that oftentimes you have a situation where the Markov chain in question, its transition matrix is not regular, and in that case, you may still have a steady state vector, but you couldn't use the theorem that we did because we didn't have regularity. And so, for that reason, wanted to revisit this using a particular example to show kind of another way of handling these things. And so a good example to illustrate what we are going to be talking about specifically is the notion of an absorbing Markov chain. This is an absorbing Markov chain is a Markov chain that has absorbing states. We'll talk about that in a second. But to illustrate this, we are going to do a very specific example. That of a tied tennis game. Okay, and here we mean a game within a set, within a match. Okay, if you know how tennis is scored. Now, I'm not going to use the actual number convention that tennis uses, so if you're familiar with how tennis is played at all, a tennis match between two players consists of some number of sets, each of which, if you're talking men's professional tennis, you're playing it like a grand slam. There's 5 sets. Each of those sets contains some number of games. Okay, and ideally you're trying to win, the most sets. Okay, you are trying to win, say 3 sets out of 5 total. Whatever, you're trying to win a majority of the sets, and to win the majority of the sets, you need to win more games than your opponent within that set. Not going to get into that because that's not important. So we're talking about a game, and within a game, how does this go? So the point is that to win a tennis game, you need to be the first to score 4 points. Now, these numbers are tracked strangely in tennis for historical reasons. So it goes 0, 15, 30, 40, and then you win if you get to that point first. But one key thing about tennis that differentiates it from a lot of other sports like this is that it is not enough to simply be the first to score 4 points. You have to be the first to score 4 points, but also you have to score at least 2 more points than your opponent. Okay, so this is the thing that this is one of the things that makes tennis the way it is, which is it is simply not enough to be the first 4 points. You need to be the first 4 points, but also you need to score at least 2 more points than your opponent. So what would happen, right, if I'm the first to 4 points and the opponent has, say, no points, then I win. If I'm the first of 4 points and the opponent only has 1 point or 2 points, I still win. But if I'm the first to 4 points but my opponent has 3 points, then before I got that fourth point, me and the opponent were tied. And this is the case that we are going to focus on. And so what we are going to focus on is the state of the game where you begin in a tied state. And the reason we do this is because this is kind of the most interesting state for the game to be in. Because, as I said, in those other states, we know how it happens, right? So if my opponent has no points and I'm the first to 4, when I score my fourth point, I win that game. If my opponent has 1 or 2 points, again, same thing. When I score that fourth point, I win. If my opponent has 3 points, when I score that fourth point, before I scored that fourth point, I also had 3 points, so we were tied, and that's what I'm getting at. So we are not tracking the entire history of the game. We're merely tracking the game once it is tied. Okay, now, if it is tied and, if it is tied at a state where a person scoring the next 2 points would win, this would be called deuce. So this is called a tie. So what are the states that the game can be in this Markov chain? So I want to use Markov chain to track possible state outcomes of tied tennis match. There are 5 possible states. What are those 5 possible states? Well, let's see. The first state is deuce, which is the tie itself. Okay, this is where we're starting in this tied match, right? The second state that we could arrive in from this is advantage A. So we'll say that we have players A and B. So there are players A and B playing this tennis match. Okay, so deuce is the tied state. State 2 is advantage A. This is A has 1 more point than B. Three is advantage B, right? Now, of course, both of these states are arrived at by State 2 is arrived at from State 1 by player A scoring next. State 3 is arrived at from State 1 by player B scoring next. So this is B has 1 more point than A. Okay. Of course, from State 2, A could score again, in which case A wins, because now A has 2 more points than B, so that's it. A has won. In the State 3, right, B could score again, which means that B wins. In State A, if B scores, now we're back to State 1. We're back to a tie. In State 3, if B scores, B wins. If in State 3, if A scores, we're back to a tie. So the next 2 states are A wins. The last state is B wins. Notice that you cannot get from state 2 to State 5 in 1 step. You cannot get from State 3 to State 4 in 1 step. But instead of us thinking out in terms of like in terms of words how this goes. Let's actually draw the Markov chain to help us here. So what we'll do is we will assume that at any given point there's a probability of P that A will score. So assume at any point there is probability little p that A will score. Now, in tennis, right, there's only two possibilities here. Either A scores or B scores. Okay? So either A scores or B scores. So if there's probability little p that A will score, what's the probability that B will score? It's 1 minus p. It's the complement. All right, so remember your basic probability theory. Right? These are the only two options. So that's what these probabilities look like. Using that, we can now draw this Markov chain. So we're going to put deuce in the middle. Right? From deuce, it is with probability p that A scores, which means this would take us to advantage A. If if A scores again, that's probability P, which would take us to A winning. If A wins, the game is over, right? But from advantage A, if B scores, which happens with probability 1 minus P, that takes us back to deuce, right? From deuce, if B scores, that's probability 1 minus P, that takes us to advantage B. Now from here, if B scores again, this takes us to B winning, which ends the game. There's one more thing to fill this out here. From advantage B, if A scores, that's probability P that happens, that takes us back to deuce. Okay. Now, what is it that is different than what we had before with our examples for Markov chains? Do you notice anything? So, in our previous examples, even when we had an example of a Markov chain that I would draw like this, that had states that were unreachable from other states, right? States that were unreachable for other states meant that the transition matrix was necessarily going to be non-regular. Okay. So we had Markov chains that had states that were unreachable from other states, but unlike this Markov chain, those processes could not end, right? So in this case, this Markov chain ends, and what I mean by that is when I get to the state A wins or B wins, that's it. It's over, right? There is no, when we had this sort of Markov chain diagram in the previous examples we did, we had like a loop here that would just like keep us here, right? But that is not technically what happens here. We just stay here forever, and that's it. Okay. Now, we could view this as a loop with probability 1. You could do that, but you see that this is really kind of a different thing that's happening here. Okay, compared to what we did before. Okay, so this modeling ends reaching either of these states. So these states are special in a way, and we're going to have a name for them that you might not be shocked by based on what I've said before. I'm going to make this a little bit slicker here, and I'll call this 1. So I'll label this 1. I will label this one 2. Label this one 3. Label this one 4. And I'll label this one 5. Okay. So 1, 2, 3, 4, 5. And just to stay consistent with how we were handling this previously, we will say, hey, this is a loop with probability 1. I just stay here forever. Same thing here. If you like, I can do that. Okay, all of these other things denote my probabilities in question. So that now I can write out the transition matrix for this thing. So I'm going to put this here at the top, and let's write out what the transition matrix would be for this. So the transition matrix T is what? So I'm going to read this column-wise. Remember what the entries of the transition matrix are. I'm not going to review that now. If you want to go have a look at our Markov chain videos, please do that at your leisure. You can revisit those videos now because that's what I'm using to write down this transition matrix. I'm going to read the columns here. So this is 0, P, 1 minus P, 0, 0. Next column, 1 minus P, 0, 0, P, 0. Next column, P, 0, 0, 0, 1 minus P. Next column, 0, 0, 0, 1, 0, and 0, 0, 0, 0, 1. Okay. Now, the first thing is I don't even need to do some kind of check here. I can actually tell just from the diagram, because of this aforementioned property that states 4 and 5 have, right? That is A winning, B winning. Based on this aforementioned property, once I get to this state, once I get to state 4, once I get to state 5, I can't leave, right? I'm there forever. So T is non-regular. So note T is not regular. Which means that I cannot use this theorem, right, that we used before. So this theorem that we used before that made this, we had this steady state vector guaranteed. The limit was always the same regardless of what our initial vector choice was. We don't get that anymore, okay? So how do I cope? Well, let's just see what happens, right? So states 4 and 5. These are states that once you enter them, you cannot leave. Okay, so it's impossible to leave once you get there. These are what we call our absorbing states. So states 4 and 5 are called absorbing states. Now, you can either look at the diagram and think about this, or you can think about how tennis games actually work. The way to think about these is that they absorb, right, the other states in the sense that eventually, if this process continues, you end up in one of the absorbing states, and then you can't leave. So you end up here or here. This game going on, you should look up the longest tennis match ever played. It's kind of hilarious. I think there was the final set, it was like 70 games to 68 games, something like that. I don't remember. I don't remember what the final set was, but it was something ridiculous like that. So it's 5 sets, and the last set alone was like longer than the previous longest tennis match. So regardless, even though that match went on a long time, and some of those games went on a really, really long time, they still always ended in either player A or player B winning. So these states are your process will end in one of these absorbing states. All of the other states that are not like this are called transient states. So states 1, 2, and 3 are called transient states. Okay, and you understand why they are called transient states, right? These are the states that you're just passing through. Okay, these are not end states. Okay. So obviously, because of how we've defined this, you cannot go from an absorbing state to any other state. You can't go from an absorbing state to a transient state, for instance. So the matrix is not regular. Okay. Now, what I'm going to do here is, from this point on, I'm going to assume a particular value of p, and then we're going to get some results out of this. But you should note that we can actually, change this around a little bit, and we will later to see how this alters what it is we're talking about. So suppose for now that p is 0.6. So that, remember, little p was defined to be the probability that player A wins. So this is saying that A has a 60% chance of getting the next point. Right? Sorry, this is not the probability that A wins. This is the probability that A scores, right, at any given time. So this is 60% chance for A to score at any given time. Rewriting my matrix T based on this, just real quick. This would be 0, 0.6, 0.4, 0, 0, 0.4, 0, 0, 0.6, 0, 0.6, 0, 0, 0, 0.4, and then 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. Okay, there we go. All right, so there's our matrix T. And now the question that we have actually is, what is the probability that A wins, given that we start at deuce? That is, we start at a tie. Based on that, why does this look so weird? I wrote that really close together. What is the probability that A wins? There we go. Right. So what is the probability that player A wins given that we start at deuce? We start at a tie. Okay. Now, if T were regular, then what we would do right now is search for our steady state vector, and we're done. Our initial vector is starting at deuce, so we know what the initial vector is. We would find steady state vector in question and be done. But because T is not regular, we can't do that. So we can't use that approach. So what do we do? We still find eigenvectors. Like, we can still find eigenvectors. Let's see if they help us. So, using MATLAB if you like, this thing has two linearly independent eigenvectors. What are they? Well, here's one. Call it V1. Okay. Here's another one. Okay. Well, these maybe don't tell us anything, at least not immediately. So then what is the idea, right? Our initial vector is the game starting at a deuce. This vector is going to track, right? Its entries are going to track the states 1, 2, 3, 4, 5. Right? So starting in deuce is the vector 1, 0, 0, 0, 0. Starting with that vector, we then define the k plus first vector to be the transition matrix applied to the kth vector. So that in this way, just as previously when we talked about Markov chains, we're in this iterative matrix multiplication process where I'm not going to write all of this out, but we've done this before. So x1 is t times the vector x naught. Here's x naught, our matrix T. Let me flash it on screen again. Remember, it's this. So this gives us x1, whatever that is, to get x2. We hit x1 with t. But of course, really, this is t times x naught. So if you like, we can have all of this in terms of that initial vector, and this would be t squared x naught. And just as before, it's powers of t that matter here, right? So that if you wanted to rewrite this entirely in terms of the initial vector, the kth vector in this process is going to be t to the k times the initial vector. So really, this is all we need. So we define this recursive process, but actually we can just find this at the kth step by finding the kth power of t here, right? So let's see how this looks using MATLAB. So let's use MATLAB here, if you like. And so what is, for x1, using MATLAB is not really necessary. You could do this one by hand. It's not too bad. So x of 1 is just t times x naught. X naught is pretty simple. Here's t, just to remind you yet again. There it is. So x1 is 0, 0.6, 0.4, 0, 0. Okay, hitting this with t yields 0.48, 0, 0, 0.36, and 0.16. What is x3? So x of 3 is obtained by hitting this vector with t. So that x of 3 is 0, 0.288, 0.192, 0.36, 0.16. Hitting this with t gives me x4, which is 0.2304, 0, 0, 0.5328, and 0.2368. Okay. So what does this say? What is this telling us? Let's maybe unpack a little bit what this is saying. So after 4 iterations, that is after 4 scores, right? So each iteration is a score, is a point scored by one of the players. So after 4 iterations, x of 4, this first entry, 0.2304, the fact that it is 0.2304 means that there's a 23.04% chance that the game is back in a deuce. So it's still ongoing. Okay? But there's a 53.28% chance that A has already won. And there's a 23.68% chance that B has already won. Okay? So this is what we get from this vector. Okay? So this means, like, just to write this out, because I think it's nice to write this out, I'm going to put this right here. So this means, i.e., after 4 iterations, it is 4 scores, there is 23.04% chance game is back in deuce. There's a 53.28% chance that A has won. And there's a 23.68% chance that B has won. Let's keep going. If we keep going, x sub 6, for instance, is like 0.1106, 0.6157, and 0.2737. X sub 10 is 0.0255, 0.6747, 0.2999, and then lastly, maybe we'll check here at the 30th iteration. This is 0.6923 and 0.3077. So after 30 iterations, that is 30 scores, there is like a nearly 0% chance that the game is still going on in deuce. There's a 69.23% chance that A has won and a 30.77% chance that B has won. Okay, so it's these two numbers really that are telling me what's going on, telling me what I want to know. And so what is it that I'm actually looking for, right? I'm seeking the thing that I was seeking before in the previous case, which is this limit. But of course, this x of k is really t to the k times my initial vector x naught, right? This is what I'm looking for. Okay. But here's the thing to note. Since t is not regular, this limit will depend on the initial vector. That is a difference with the regular case, right? So this depends on that initial vector x naught. This is something that didn't really happen in the regular case, right? We went to great lengths to show that it didn't actually matter which thing we chose. We still got, in the end, we got the same thing. That's not true here. And it's not true because of this non-regularity of the transition matrix. Okay. So what this example showcases is exactly this property that I was talking about of absorbing Markov chains. So what is an absorbing Markov chain? So in a Markov chain, an absorbing state is one in which you get stuck forever. Okay, so you get stuck forever. All right. By an absorbing Markov chain, what we actually mean is that it's a Markov chain that has at least one absorbing state. Okay. And the point that maybe I should go and write out, so by absorbing Markov chain, we mean a Markov chain, I'm just going to write it as MC, that has absorbing states, and it is possible to get from any transient state to some absorbing state in a finite number of steps. Now notice this doesn't mean that you have to be able to get to all absorbing states, right? Maybe some absorbing states are only reachable from certain transient states, blah blah blah. Okay, but this is what we're assuming. Okay. So, suppose that we have a Markov chain, we'll call it M, and it has R transient states. We will call those T sub 1, T sub 2 out to T sub R. We'll say that it has S absorbing states. We'll call this A sub 1 to A sub S. So then it has R plus S total states. Okay, we're going to write these R plus S states in, we're going to order them transient first, so T1, T2 out to T sub R, and then A1, A2 up to A sub S. So there's R plus S of these. The transient matrix then will be put in block form. So this allows us to put the, sorry, not transient matrix, transition matrix, same root word, into block form as follows. Maybe I'll put this on the next page because, well, no choice here. I've run out of page. Okay, so what does this transition matrix T look like? It looks like the following. It's a block matrix where there is a block we'll call Q. This is going to be an R by R matrix. I'll describe what Q is here in a second. Then we're going to have R, which is an S by R matrix. Then we are going to have a matrix of zeros, which is going to be R by S. And if you're keeping track here, if this is going to be square, this now needs to be S by S. And that's the S by S identity. So what are these matrices? So Q, that is an R by R, holds the probabilities of moving from a transient state to another transient state. So probabilities of transient to transient. Okay, what about this thing? This is probabilities of moving from a transient state to an absorbing state. Okay. This is a zero matrix. That's R by S in size. What are these zeros? Why are they zeros? Because these zeros represent the probabilities of moving from an absorbing state to a transient state, which are all zero because you cannot move from a transient state, or sorry, from an absorbing state to a transient state, right? And then this is the S by S identity matrix. Why is it the identity matrix? Well, these probabilities contain, or the probabilities therein are the probabilities of transitioning between absorbing states. Now, you, of course, cannot move from an absorbing state to another absorbing state, but for the purposes of, interpreting this, we did consider staying in the absorbing state forever to be the same as moving from the absorbing state to itself forever with probability 1. So that's where the ones on the diagonal of this identity matrix come from? Okay. So remember, in our tennis example that we just did, what did our transition matrix look like? We had 2 absorbing states and 3 transient states. So here's Q, here's I, right? So this is Q, this is I, this is R, which is a 2 by 3 matrix. Q is a 3 by 3. I is a 2 by 2 because there's 2 absorbing states. And then this is a 3 by 2 matrix of zeros. Right? So this was exactly the form that this block matrix or this transition matrix takes. This is how the blocks work. Okay. Now, what is the purpose of this, of blockifying this thing? So, in general, in linear algebra, the purpose of writing a matrix as a block matrix is that it makes matrix operations easier to do, and typically, especially if you have huge parts of the block that are zero or identity matrix or whatever, it really makes things much, much easier, right? So, an extreme example of this is like diagonalizing a matrix, right? Or, maybe something a little bit fancier, of which diagonalization is kind of like a special case, is Jordan canonical form, which you may or may not know about, but that's okay. We don't need it for our purposes. So what does this allow us to do? The idea, this makes computing this limit of these powers of t times an initial vector easier. Okay? To see how this works, what is t squared? I'm going to write it out here fully. I'm going to write it out. So this would be QR0I times itself. You can check that these dimensions all work out for what I'm about to do. When I do this, what do I get? I guess be careful with how this goes. I get Q squared. I get RQ plus R. I get zero matrix of the same size, R by S, and I still get my S by S identity. Okay. So that's nice. This is t squared. What about t cubed? Well, t cubed is really just, if you like, t times t squared. So it's this times this, which I'm just going to go ahead and skip and write that. What is that? This would be q cubed. Q cubed. That's a funny statement. Then this would be RQ squared plus RQ plus R times, or sorry, in this entry this would be zero vectors, or not, I mean, yes, all these vectors in this matrix zero, but it's a zero matrix of size R by S, and still the S by S identity. Maybe one more to really settle this down. What's t to the fourth? Same thing. This is like t times t cubed, and now I know what t cubed is. So this is q to the fourth. This block would be RQ3, or sorry, RQ cubed plus RQ squared plus RQ plus R. You see what's going on here. Zero matrix, it's R by S, and the S by S identity. Okay. Good. All right, we're happy with that, you can see what the pattern is going to be here. So I'm going to go ahead and write out that pattern. Notice how nice this is, because trying to come up with like a generic formula for matrix powers in general is like really garbage, right? It's really bad. So t to the k in general, following this pattern, is a block matrix where this block is q to the k. Now that's still, you got to figure out that matrix power, so you're like, maybe this, how does this help me? And then I'm going to write this as like r plus rq plus rq squared, and so on up to rq to the k minus 1. That's the pattern here, and then 0, and then I. Rewriting this in a simpler, more suggestive form here. I have this block is q to the k. This block, I can factor this r out, right? So matrix multiplication, it's not commutative, but it is distributive and it's associative. So I can factor this r out. So this is r times the sum of matrices. We'll call this q to the 0 here if you like. So this would be I equals 0 up to k minus 1 of q to the I. And these two slots are the same, so 0 matrix, it's R by S in size, and S by S identity matrix. This does it. Okay. Now, here's the thing. When we take this limit, so I want to take the limit as k goes to infinity of t to the k times some initial vector, right? When I take this limit, I'm going to have to deal with this sum. Right, so obviously I'm going to have to deal with a q to the k, but this sum is actually more tricky. If I can deal with this sum, that I'm dealing with q to the k is not going to be a problem. So I'm going to have to deal, I must deal with, when I take the limit as k goes to infinity, this sum becomes an infinite sum, which looks like a geometric sum, right? Q to the 0 is the identity matrix, plus q squared plus q cubed, and so on. This infinite sum. Now you might say, well, this isn't a geometric series. Like, these are matrices. These aren't, numbers. Yeah. Remember, when we dealt with this before, we used a formal inverse of this thing to explain like what it is we're doing, and then showed that under certain circumstances that formal inverse worked, right? That geometric series formula actually worked, right? So so under the assumption that the column sums were less than 1, we saw previously that we could actually compute this as 1 over 1 minus q, right? So this would be 1 over I minus q in that way, right? This was our formal thing. But of course, what this actually is I minus q inverse, right? And when I say equal, maybe I should say converges to. We'll be precise here. Okay. But let's look at this tennis example that we had. The Q in question is this thing, and these two columns have sum less than 1, but this column's sum is equal to 1. So it's not strictly less than 1. So what do I do? Right? So in our example, Q was like this thing. So this is, not less than 1. But what about q squared? If we look at q squared, I'm going to read column-wise. This is 0.4800, 0, 0.24, and 0.16, 0, 0.36, 0.24. So this is what I get. So q squared, all of the column sums are less than 1. This is also true for the higher powers, but q squared works here. This is going to be enough to guarantee convergence. And in general, if it's true for some power of the matrix, then that's enough to guarantee convergence. Okay, so some power, q to the k, has to have a column sum less than 1. And this convergence works. Okay, so we are good here. Okay, just to repeat, in general, if some q to the k has column sum, all column sums less than 1, the convergence works. Okay. Now, this q to the k is the upper left block. This lower left block is going to have non-zero entries in each column for large enough k, just by the definition of absorbing Markov chains. And so, putting all of this together, we have the following theorem. Okay, or maybe I'll write it as a pair of theorems. It might be better to organize it this way. So for an absorbing Markov chain, some power q to the k will have a column sum less than 1. Thus, in this case, this infinite sum of these q's, which you could write out like this, this infinite sum is actually the inverse I minus q. Since this sum converges, individually its terms must go to 0. This is called the nth term test, right? If you remember that from series. So this series converges. Its terms must go to 0. Okay, so this is the nth term test for series. Thus, this means that the limit as k goes to infinity of this q to the k is actually the R by R 0 matrix. If you like, this is the nth term test for series. So that handles the upper left block of my matrix. And so, putting all of this together, we have the following. For an absorbing Markov chain, with transition matrix that looks like this. Right? All of those having the same. Here, this is R by S. This is S by S. You can tell what these have to be based on that. We have the limit as k goes to infinity of t to the k is this upper left block, remember, is this q to the k, so that's R by R 0 matrix. This remains the R by S 0 matrix. This remains the S by S identity. And then lastly, this is R. Right, remember here, let me put it back. Right, what we had for t to the k. T to the k is this thing. I factored R out, so I'm dealing with this, and R is multiplying the result here, so it's going to be R times I minus Q inverse. So that's the kicker, right? This is the big thing. Okay. So let's go back to our example and apply this theorem. So example, our tennis example from earlier. In our tennis example, we had all of these quantities. So just to remind you, where did I box those? There we go. So for our tennis example, here was our Q. Here was our R right here. And of course, this is zero matrix. Here's identity matrix. So what do I need to compute here? Let's just compute directly in MATLAB. So here's R, here's Q. For our example, using MATLAB, the 3x3 identity minus our matrix Q, if we find the inverse of that. MATLAB tells us this is, I'm going to read column-wise here, so this is 1.9321, 1.1538, 0.7692. Next column, 0.7692. 1.4615 and 0.3077. Last column, this is 1.1538, 0.6923, and lastly 1.4615. Okay. So then multiply this by R, so R times this is going to be a 2x3 matrix. I'm going to read column-wise here. So this is 0.6923, 0.3077, 0.8769, 0.1231, 0.4154, and 0.5846. This is going to be the lower left block in our matrix. So then what is the limit as k goes to infinity of t to the k? I'm going to put it in the matrix, although all you need is here. But I'm going to put it in the matrix to show you what this means. So everything is zeros. To the last two rows. Then we have this thing. Just going to copy. Here. This is what I get. Now, what does this tell me? Suppose game starts in deuce. Of course, this corresponds to a choice of initial vector. It looks like this. What would I do to find the probability of what state we are in after a long time? I would compute the limit is k goes to infinity of t to the k times x naught, which if you do this multiplication, what do you get? You get a vector 0, 0, 0, and then you get these the entries in this first column here, 0, 0.6923, 0.3077. So what does this mean? So 69.23% chance A wins and 30.77% chance B wins. Notice this is the original question that we actually wanted to answer, right? The probability that we started with, little p, was not the probability of A winning, it was the probability of A scoring, right, on a given point. So this basically answers like everything that I wanted to answer about this problem, right? This is pretty much it. Okay. So you might say, well, the fact that you're multiplying by this initial vector is just extracting this first column. That's exactly what's happening. But notice right here, what do these numbers then mean? What if I had started in my initial state 0, 1, 0, 0, 0? That would be advantage player A, which tells me that if we started with advantage player A would win 87.69% of the time, and player B would win 12.31% of the time, given that player A was scoring on 60% of a given point. If we had started with advantage player B, we'll notice that it's 41.54% chance that player A wins and a 58.46% chance that player B wins. So that is what this is saying. Of course, you might say, what about these entries? These are saying if you're starting with the initial condition that A has won, then of course A wins with probability 1. If you're starting with the initial condition that B has won, then of course B wins. So it's very clear, right? Like this tracking which state we're starting in here is you basically don't even need to do that. You can just look at it from this limit matrix. Okay. So what we just figured out there in words, I'm going to write that down in a couple theorems, and then basically we're done since we've pretty much described everything that we want to describe here. So next statement. So for an absorbing Markov chain, the ij entry of R times I minus Q inverse is, and if you like, I mean, this identity matrix is R by R. So what is this? This is the probability of ending in absorbing state A sub I, given that we started in transient state T sub j. Now recall that when we did this before, we actually got even more info out of this, right? So we got even more info out of the matrix in question. So I'm going to write one more theorem here. So what about the matrix I minus Q inverse? So under the same assumptions, I'm not going to rewrite it. For an absorbing Markov chain, we have the following. The ij entry of I minus Q inverse contains the expected number of visits to transient state t sub I, given that we started in transient state t sub j. And lastly, the jth column sum of I minus Q inverse contains the expected number of time steps before absorption. Given that we started in transient state t sub j. Okay. So let's return to this example that we wrote out and interpret this theorem. So let me oh yeah nope let's do it like this. We really bend it. Okay, there we go. Now here's the matrix in question. Computed this. According to this theorem, this first entry says that if the game starts in a deuce, then the expected number of times it will be in deuce is 1.9, or 1.9321. Okay. Notice this counts the starting deuce. Because of that, all these diagonal entries, because they're tracking a similar thing, should be at least 1, and they are. Okay. The expected number obviously is the same as it's the same notion as expected value, right? So this is a weighted sum that you can think of as the average here. So that if we played 50 million games of tennis starting in deuce with the probability on any given point that player A scores, the expected number, right, on average of how many deuces we would have per game would be 1.9321. Okay. If I sum the first column, this sum is 3.8462. So what does that first column sum tell me? Assuming the game starts in a deuce, it will take on average 3.8462 scores until the game ends. So, for example, if A and B play 30 games of tennis and we assume there's a score every minute, we should expect that they play for a total of 30 games times 3.8462 scores, 1 minute per score, about 115 minutes. Okay. Again, this is starting in a deuce, right? You could answer all of these questions starting in any of the other states by summing other columns, for instance, right? Or by looking at other entries and what I was doing first. Okay. So, one thing I'm not going to actually, you know what? Maybe I will. So we can actually work out our tennis example entirely in terms of P. So for our original To this example, let me rewrite this. We had our transition matrix T, which was reading column-wise, this is 0, P, 1 minus P, 0, 0, 1 minus P, 0, 0, P, 0, P, 0, 0, 0, 1 minus P, 0, 0, 0, 1, 0, and 0, 0, 0, 0, 1. So that Q is this block. And R, of course, is this block. So that before we even assign any value to this P, we can actually work it out entirely in terms of P. So using MATLAB again, what does this inverse look like? I can work this out as 1 over 2p squared minus 2p plus 1 times the 3 by 3 matrix reading row-wise 1, 1 minus p, 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 p squared minus p plus 1, p squared, 1 minus p, 1 minus p all squared, and p squared minus p plus 1. Okay. And multiplying this by r, what I get is, still going to get this thing out front, so this would be 1 over 2p squared minus 2p plus 1 times the 2 by 3 matrix, p squared. I'm going to read row-wise again. This is p squared, p times p squared minus p plus 1, and p cubed. Second row, 1 minus p all squared. Next is 1 minus p cubed. And the last one, 1 minus p times p squared minus p plus 1. So how do I use this to answer the questions that I have purely in terms of p? Right? Remember, little p is the probability that A scores on a given point, right? So what about the expected number of scores before the game ends? This would be the first column sum, right, of this thing. So, for example, expected number of scores before game ends would be first column sum of this thing, which would be this. Of course, I have to scale it by this thing. So it would be 1 over 2p squared minus 2p plus 1 times this column sum 1 plus p plus 1 minus p. So that'd be 2 times that thing. So it would be 2 over 2p squared minus 2p plus 1. You could answer similar questions similarly with either column sums or looking at the entries. So I'll leave it up to you to play around with some of those numbers to see how this works. So for instance, when the probability is 0.5, so A scores 50% on the points, which means that player A and player B are perfectly matched, The expected number of scores before the game ends is 4. Since we're assuming we're starting on deuce, why does that make sense? Right? Does that make sense that the expected number would be 4 if the players are absolutely evenly matched? You can think about that. Okay, but that's pretty much all I wanted to say about absorbing Markov chains. So I think I will stop here. And this example is a really, really good one. There's a lot of questions that you can ask here that really kind of like fully encapsulates what's going on with these things. Obviously, you could cook up scenarios where your Markov chaining question is more complicated, right? Like I said, maybe you have absorbing states that you can't reach from every transient state. There's a lot of things that you could do here to modify this and make it interesting. But it's already plenty interesting. So anyway, this is it. This is absorbing Markov chains. So I will end here, and we'll be on to the next topic. So I will see you next time.